Bene, good. So, lesson number, I don't know. Last time, 17? Wow. Last time I completed the definition of the theory. So, let me summarize the theory in this formulation. This is LQG in just a few equations. There is a kinematic part in which we work in terms of Hilbert spaces associated. A graph is with the notation I introduced SU2 to the L over SU2 to the N, where the action of the gauge on the group element is given by the graph. So the states are functions on this group element, and there is a bunch of operators. The most important one are associated to the links of the graph, and they satisfy the SU2 commutation relation for the same link. So delta L L prime epsilon ij k L k L. So this is the kinematics, which we did before, and the dynamics can be summarized in one equation or two equations. So in this Hilbert space, there is a vector, or more precisely a bra, so a linear map from this Hilbert space to the complex number, which is the amplitude, which I write as W. I don't remember if I used A or W. So it's in this space, so it's a function of the HL, and it's written as a bunch of integrals over SU2 element, which depend on the vertices and faces of a two complex, and is just the product on the faces of the delta function of these around the face, product of the faces of the delta function of the product of the H VF around the face, so the various vertices around the face, and then a product on the vertices of a vertex amplitude, which is the main object of this thing here. And the vertex amplitude is a function of SU2 group element, of the group elements around it, which are associated to faces, and is an integral on SL2C element, SL2C elements associated to the edges that come out of the vertex, and a product of what of one piece per each face that come out of the vertex. So the product on the faces that come out of the vertex of 2j plus 1. I hope I haven't. Sorry, of a sum. It's not j yet. A sum over j spins from 0 to infinity, half integers, 2j plus 1. The trace in the j representation of, so we have a face here, h of that face, and the two SL2C group elements that come out of the face, which I call GE prime, oriented appropriately, so that this makes a turn, and this is y gamma dagger. Okay, where I gave explicitly the meaning of this formula here, just the product, the contraction of two matrix elements, one for SL2, one for SL2C. So that's it. That's two quantum gravity in one page. Let's put this. Let's do a little bit more clearly what are these indices meaning. The kinematical part. Let me use a color code. Let's see if it works. I have a graph, and and so on. This HL sits on the links of the graph, and the gauge transformation sits on the node of the graph. So these are the link and the node. So the group element sits here, and so on. And this HL these are oriented, so are associated to each one of these link. This depends on a 2 complex. Let's put explicitly the dependence of the 2 complex. Try to see here for a 2 complex. What is a 2 complex? It's a collection of vertices, and each vertex has 5 edges that come out of it. So this is an edge, this is an edge, this is an edge. Let's say there are 5. I do less than 5. And then there are faces. So this is a face. This is a face. That's the way you can think about. This is a face. Let's say there are two other vertices behind, one other vertex behind. So I also have a face down here, a face down here. And these are 3 coming out, 1, 2, 4 coming out of this. You think they're 5, but it's harder to draw. The point is that on the boundary of the 2 complex, there is a graph such that each face here, say let's look at this face here, is bounded either by internal edges, this E here, or by a link of the graph, one of these. And the edges bounce on the node of the graph. So each vertex here has around it some edges and some faces, and each face has 2 edges which are its own brother. So each HF here is related to edges, and here I have the group element associated to this face and the SL2C element associated to the two nodes. For its vertex, I'm integrating on all the SL2C elements sitting on these edges, and around this edge there are all the SU2 element. So I integrated the SL2C element here. There are these SU2 elements, which for the internal faces, if you're inside the 2 complex, so you just put a delta function. If you're on the boundary, this is the boundary in the spin network boundary, right? This is the way things is together. This is how the theory works. A couple of observations before going ahead. One is that this is written on the basis, the states here are written on the basis of the group element. But of course we have also defined the spin network basis, where instead of for a graph gamma, instead of the basis of the group element, there is the basis JL Vn, where V is some basis in the Twiner space. It could be the one that diagonalizes the volume or other. And the relation between these two, forget the gamma for a moment. No, let's write the gamma. Forget the gamma. Is JLVN is the DJL HLN, all the indices here. So the product of all these on the links contracted with the products of all the intertwiners on the nodes, where the free indices here are contracted with the free indices here in the way the graph dictate, right? So you have a matrix here with an index here and an index here, a matrix with an index here and index here. For every node, you have an intertwiner with an index for each one of these. You contract of them. This is the basis. So one can change basis from here to here, like when you go from the x basis to the p basis, and the analogous of this formula is xp is e to the I px, right? The same thing for function of the group instead of function of x. So this can be obviously translated in the spin network basis by simply inserting the solution of the identities. So I can write this we did in the spin network basis, but I can rewrite this as an amplitude on the spin network basis by simply integrating on this SU2 element and putting a solution of the identities with this, and I get an expression which it's entirely in terms of spins and intertwiners without group elements, and it's not too hard to do it, to work out, which is just a simple property of the of these matrices here. If you want to see how this works, try to do it. It's in the book, so you can try it, and if you fail, you see how it works in the book. There's a little rearranging of terms, but essentially what happens is very easy. At the end, you get an amplitude, this amplitude here, W, which is a function of the spins and the intertwiners, right? Because you go to the other basis, and it turned out to be given by a sum over spins associated to faces, to internal faces, and intertwiners associated to edges. Okay. Of some product in J face to J plus 1, which comes from this term here, which just goes together, and a product over vertices of a vertex amplitude, where the vertex amplitude now is a function of the JL and Vn sitting around its vertex. Now each vertex, there is a spin here, there is an intertwiner here, a spin here, an intertwiner here, a spin here, an intertwiner here, right? And if you have a proper 5-valent vertex, let me try to draw it a little bit. There are 5 nodes around, so 1, 2, 3, 4, 5. So you have the spin network around it, which is this spin network here. Okay, which happens to be the symbol of the Red Brigades in Italy in the 70s, but it's not supposed to be related to that. You have edges that come from here to here, and you have faces in this way here. So this object here is the main object of the theory. Is the amplitude of the vertex is a function of 10 spins and 5 intertwiners. Right, this is the key object, and it's written explicitly in terms of this SL2C integral. So in terms of this Wigner matrices for SU2 and SL2C, and we know its property when J is large pretty well. That's one thing I'm going to do explicitly. I'm going to show you, and we don't know very well. We don't know much what happened for small J. There's a lot of numerical work, people with computers who are computing this explicitly here in Bilbao and elsewhere, both in special cases and the general case. So for generic spins and intertwiners, how does this behave? So again, we know the large spin behavior, so we know what's supposed to happen, but it's not totally clear what happened in the deep quantum regime, which is small small spin, right? And the simplest way of doing classical limit is what Bohr did. The classical limit is large quantum numbers. So large quantum numbers means you're away from the discreteness of the theory. So there are now computer codes that compute this up to j equals something. The complications is that there is this SL2C integral, so one have to do it to do it. But there are techniques. I'm not going into that. A particularly simple way of writing the amplitude in a schematic way, which I find telling, is sort of tells you what happens. You can think that this Y map that I gave explicitly, it's a way to map. You can use it as a way of mapping function of SU2 to function of SL2C. Just immediately use it to. If you have a function of SU2 with a Y map, you can get a function of SL2C. So if around the state around the vertex, it's a function of SU2, right? Because if you view it in the SU2 basis, it's a function of SU2. With this Y map, you can map it in a function of SL2C, and this is what is happening here. And then once it's a function of SL2C, it's an SL2C spin network, essentially, which is not invariant on the nodes because you started from something which SU2 doesn't know anything about SL2C. If you integrate on the action of SL2C on the nodes, you project it down to a proper SL2C spin network, something invariant under SL2C. So you can write these integrals formally as a projection on the SL2C invariant part of the state as a function of SU2 mapping SL2C. And then what you're doing, the amplitude of this, if you think for a moment, is that, the amplitude of the state is, here you have an SL2C invariant spin network. If you compute its value on the identity, you get exactly this formula here. So it's a correct but very compact way of writing this formula here. So in a sense, the amplitude, the core of generativity is take SU2 spin network, map them to SL2C spin network, make them SL2C invariant, compute it amplitude. This is going to give the action, the Einstein-Hilbert action in some limit. So you can think that the full theory is given by these two equations and this nice, pretty equation here. That's the core of the theory. And when I was young, I remember I read, never take a theory seriously unless you can present it compactly enough to write it on a T-shirt. And that's the T-shirt. And it's hot. So, I don't sell T-shirts. I don't money this way. It's not an advertisement. This is not an advertisement for selling. Yeah. 5 copy of my book. You get a T-shirt. Good. So that's the theory. Of course, is given very abstractly like that, and you start understanding it when you work with it, and when you prove things with it. So let me say a few general things about it, just to orient you. First of all, there is a sense in which there is locality. Right? Remember, these fields don't live in a space-time given, but this is a quantum of space, right? This is a blob, which is a minimal piece of space. It's a blob, which is a minimal piece of space. This is a quantum of space, and you can view this as a discretization of space, and this is a discretization of space-time. So this is the dual. I introduced as a dual of 4 simplex. You can also view as on the boundary of 4 simplex we have 4 tetrahedron. You have 4 tetrahedra, 1 tetrahedron splitting into 4. That's the way you can think about it. So it's a history of space-time quanta, and this is a representation of space-time. In fact, you can associate a 3 geometry to the data of a spin network. You can associate a 4 geometry to the data of a spin foam. If we have time, I'll go into some detail. And the amplitude, the total amplitude, is just a sum over geometries, over configuration of something which is a local product of amplitudes, which is what you expect from locality, right? You expect something like the functional integral of some field, e to the IH, an integral in space, in d4x, of some action, or some Lagrangian. And e to the sum is the product of things, right? So e to the sum of things is the product of e to the to each one of them. So this product of the vertices here is like is e to the sum of that. Theory is local. Things happen each interacting with the next one. There is no long range interaction. Is the F-tail Lorentz invariant? There is Lorentz invariance in the theory. There is explicit Lorentz invariance introduced by the Lorentz transformation. And on the boundary, there are the states which are SU2 written in the time gauge. But if one really wants, one can go to a fully manifest Lorentz invariant formalism on the boundary by getting out of this. And one has proper SL2C spin network on the boundary. There's nothing one really gain except writing this manifested. It was done some time ago. The theory is ultraviolet finite. We'll see explicitly because in these sums here over spins and intertwiner, we're summing over dimensions of things. These are like in 3-dimensional J are the areas of things, and you sum with arbitrary large dimension, but you stop at small scale because J start from 0, 1/2. So there's nowhere this can be reproduced if I'm an integral for high momentum, because there's no small space here. Space is discrete. In fact, the entire reason of being of this is to have discreteness and Lorentz invariance together. That's the game of having discreteness, Lorentz invariant together. As we discussed at very length, the amplitude do not have a time variables in which they evolve because there's not supposed to be a time variable in which they evolve. This is initial 3 geometry and a probability for a final 3 geometry. If you do the classical limit, this corresponds to a 4 geometry in the middle in which you have all your proper time along line that you want. There are a number of theorems that relate this to GR. I want to get to this theorem, but before that I have to talk about coherent states. So this I will do that tomorrow to show why this strange equation here actually knows about generativity. And there is a number of indirect arguments that show that this is GR. I just list them. There's a long literature on that. The endpoint functions of GR have been computed starting from this equation here. In cosmology, the Friedman equation has been derived starting from this amplitude in some approximation, and so on and so forth. There is a large amount of work. The Bekenstein Hawking entropy has been derived in zillions of times using that, and the recent work which we've been doing here is to compute tunneling probability for black holes going to white holes. Black hole to white hole tunneling probability. You have classical space-time. You have a collapse of a star, of something. A lot of time passes, so you want to know what happened in the future. At some point, there can be a quantum tunneling, some region where classical equations are violated, and we have studied the possibility that at some point the black hole tunnels into a white hole, and what is inside comes out using exactly these equations here. Fabio and Marius have a hard-worked paper on that, just basic on this on these equations here. I should, of course, I have not mentioned any names behind all this work. If I had to start to give credits, there's a huge number of people who are behind this equation, starting from the Asheka, Smalling, Lewandowski pooling of all team, and of Barbero for the work setting up the sort of the first era of the LQG. But specifically, this equation here come from not a few people, many people. I mean, here there was Jonathan Engels, who is now in the US. Roberto Pereira, who is now in Brazil. There was Simone Speziale has worked on that. Levin, Laurent Friedel has worked on Kirill Krasnov, and the Polish group, Lewandowski and all his collaborators, which have Polish unpronounceable names for me, Kamiński, Kielowski, and etc. So it's a collaborative thing. In fact, these equations came out in various versions, and then they were sort of converging together.
These things you say it gives the Friedman equation. Is it like a concrete that from this definitely this sort of Friedman equation comes about, or is you do you have you discretize the universe. You see how it evolves with this thing here. You compute evolutions, and you discretize it in very rough discretization, because the Friedman equation is only 1 degree of freedom, if you want, and out of that you do some manipulation, and you see how the scale factor changes with respect to some other variables that you have around, and you get the Friedman equation from. So there's no ambiguity like in string theory where you can predict multiple results from the individual.
Good. I'm getting to that. The theory I've defined is. It's just one, right? There's nothing ambiguous. This is it. Then you can compute it's either right or wrong. And in fact, there is no free parameter in it. Of course, there is a free parameter because there is h bar g written. This is in as I've written it is all dimensionless, but to connect to meters and seconds, you have h bar g. So it's just one parameter here. If you add matter, h bar and g separates, so you have h bar and g separated because g comes into the coupling with matter. So there's no ambiguity. There are no zillions however, this is not a God-given theory, and all sorts of variants have been studied. There's a number of, in fact, this next thing I wanted to talk. There's a number of variants, and I've given you one version because it seems to me the easiest to work with and the one I'm working it. But I myself switch between various variants of the theory. We don't control the theory well enough
to be sure that this is a final version or anything like that. And one variant which I've mentioned is that I've only talked about triangulations. So tetrahedra and four simplices, but there's very little, in fact, which is attached to these graphs and these two complexes being dual into triangulation. All the equations make perfectly sense if you go to general graphs and general triangulations. And in fact, especially the Polish group has made this point very explicitly. And there are reasons to go to general graphs which are not dual to triangulations, and in particular have arbitrary valence. Especially if you come from the old canonical theory, in which these loops were just arbitrary loops in space meeting in intersections. That was Lewandowski's original suggestion. Y should be four valent. So you can go out of triangulation and have general graph, general two complexes. A lot of what I've said remains, and in fact it's quite interesting how it remains. If you have a node with not four but more than four links, then obviously you cannot interpret it geometrical dual to a tetrahedron. But there is a theorem, it's called Minkowski theorem. It's a theorem dual Minkowski. It's the same Minkowski, but it's nothing to do Minkowski. Nothing to do with Minkowski geometry. The theory says that if you have a polyhedron, I'm not very good in drawing polyhedra, and you have the normals, and you know the normals. You have n vectors. Okay, you have n three-dimensional vectors, and if you know that these vectors are normal to the faces of a polyhedron, and their length is proportional to the area, then this determines the polyhedron uniquely. So in fact, it's stronger than that. If you have n vectors which satisfy the condition sum of all of them, that all this sum of all of them sum to 0, it's sufficient to have an arbitrary number of vectors satisfying this equation here, and the theorem says that there is one and only one polyhedron that has the shape such that these vectors are normal to the faces and the length is proportional to the area. So the L operators sitting on the links of an arbitrary graph do define a geometry of this polyhedron instead of. So many things generalize like that. Some are harder, and the classical limit is much harder, and it's not obvious. It goes by. So this is one variant, which it's definitely interesting, especially because when you wanted to use the theory and do calculations, and you want to discretize pieces of space-time, to do it with triangulation can be very hard, as somebody knows here. So it's easier to say, forget the triangulation, just discretize it in a more general way, and the theory can be taken in this manner. In the equation itself, you can twinkle with this equation, right? The classical limits, especially what is well controlled, is the amplitude of the vertex. But this 2j plus 1 here, you can put a mu here and have mu different from 1. In fact, there are arguments that were produced in Poland for mu equal to 2, and if you compute the infrared divergences of this, they are 0 provided this mu has a certain value. So there might be good reasons for twinkling with this mu here. Sort of like it's like changing the measure here with the same action, something like that. And in fact, you've been studying the possibility that for some particular value of mu, there is a sort of scaling variance, and you can refine the triangulation, and the expectation value of operators don't change. So it's and other things. I've done everything without matter, but matter can be coupled to that. I'm not going into that. There's something in the book. There's not much literature on that, but something there is. And finally, last comment. There's a version of this with cosmological constant, which I'm not discussing because it requires a little bit more rich mathematics. But it's a twinkling of this, which makes it also infrared finite, not just. So with a cosmological constant, there are theorems in the version with cosmological constant such that these quantities are finite, mathematically finite, rigorously finite, not physicists waving hands and saying, well, shouldn't diverge. It really does not diverge. So before going ahead, I want to clarify a crucial point, which is the absence of parameter there, because it's what explains why things work. You see, if you think this amplitude here, you can put a mu here if you want, but again, this is like changing the mu. What is striking here is that I haven't told you that there is a parameter to take the critical point. And everybody who does QCD on the lattice, approximation of a quantum theory with a discrete thing, knows that you should tune a parameter to a critical point in order to go to the continuous limit. And I haven't said anything about that. Why? This is a core of the theory. This is how diff invariance, lack of a background, comes into the quantum theory. So let me go it slowly and correctly. Let's go back to Feynman thesis, because that's all start from there. Feynman had the idea that if you want to compute the propagator, let's say the propagator, you do a functional integral, let's say q of some action, one-dimensional integral in dt of a Lagrangian, which is a function of q and q dot. Okay? But of course, what does this mean? This means, in Feynman theory, path integrals in quantum mechanics are all over, but concretely, they mean either a way to juggle with perturbation theory and do equations with all the terms of perturbation theory, or you discretize them. So it's a limit. This is the limit, and this is how it was defined in Feynman. And what limit exactly is what I'm going to discuss of the discretized version of this. So you take time. This is time. Here there is timer, very Newtonian things. You do this from some initial time to some final time, say total time, big T or whatever, and you break it, time in n little steps, and each one is epsilon, so is T over n. Okay. And what Feynman did is to take this thing here, e to the h t q prime, and break this into a product of e to the h epsilon, right? Many of these. Insert resolution of the identity. Each resolution of the identity gives an integral, so you end up with a multiple integral dqn. Qn is this variable here. And then you do the calculation of this transition amplitude for a little step, for small epsilon, you approximate, and you discover that it can be written as a discretization of the action. So a sum over n of some ln, which depend on all the qn in some manner. Now, let's do it concretely for a, say, harmonic oscillator. So L is 1/2 q dot square minus omega square q square. Okay? Now, q dot square, that's what you have to discretize. Q dot, you discretize by qn plus 1 minus qn divided by epsilon, of course. Okay, the derivative is this difference between here and here, divide by epsilon. This is crucial, this point. So the discretized action here, this thing here, S discretized with big N, is what? Is the sum over N dt, which is epsilon in the discretization, and then q dot square, so qn plus 1 minus qn over epsilon square, minus omega square qn, everything multiplied square. Right? So we are integrating over qn the exponential of e to the h, this thing here. Now, it's convenient to, let's do that. Let me put this square only upstairs. So there's an epsilon square here that it's this one, and I have an epsilon here. Epsilon goes here. It's convenient, and what one does all the time to get rid of this epsilon downstairs. This is an integration of qn, so I can change variable. I have a q star, a q tilde, which is this by square root of that. Okay, so I just change my integration variables. I take this away, and I get a square root upstairs, but there are two of here. I get an epsilon squared there upstairs, if I'm not wrong. So what I get is the amplitude as the limit of the integration in dqn. I can call it qn or q tilde, it doesn't matter. Integration variable, the sum over n of qn plus 1 minus qn square minus epsilon square omega square qn square, right? And it's a good idea to call this omega epsilon, I don't know. So let me actually call it omega epsilon. The point is that there's an epsilon in its belly, right? And I'm summing from 0 to n, from 1 to n. So I'm taking the limit for n going to infinity, but I have to remember that is also omega epsilon going to 0, right? And the key point is that there is this one. So the path integral gives back the continuous theory, provided that a parameter is taken to a critical value. This is happening all over in the discretization and getting back to the continuous limit. If you do QCD on a lattice, it's exactly the same thing. You have the Yang-Mills theory, you have a lattice, you discretize the Yang-Mills theory as a group element of the link. The Yang-Mills action is f mu nu, so you want to approximate f mu nu, you take the u around the plaquette, right? For small lattice size, the u around the plaquette is the identity plus f square. So you get the action out of that. You write the action in terms of the plaquette, but this is 1 plus f square with a square, a being the lattice space. So you have this a that floats around, which if you write in the action, it sits in front of the action. So when you do lattice quantum field, lattice QCD, in front of the action, you have a coupling constant. You have to take to 0 to get to the continuous theory. You have to go to the critical point. All right, this is what is written in all the books. But let's do exactly the same game in a context in which you use a language without background time. So let's take the same system, this system here, harmonic oscillator, but let me treat Q and T on the same ground. So I have both of them evolving in some parameter tau. Remember that if we take q and t in the same ground, we can evolve them in a parameter, which is unphysical. But that's how general relativity is formulated, something evolving in a physical parameter time. And uses a Lagrangian, okay, as an action. So my new action is going to be the integral in d tau of a Lagrangian evolving in tau. What is this action that gives the same motion of the harmonic oscillator? Well, it's the same Lagrangian here, is the harmonic oscillator Lagrangian, rewritten in terms of tau. If you think for a moment, it's obvious. You write here dt over d tau, and then q dot is dq over dt, so you write it as dq over d tau times 1 over dt over d tau, all this square, minus omega square q square. So let me call q dot and t dot the derivative with respect to tau, so this is a less cumbersome notation. This is d tau. T dot, I have a t dot downstairs, so I have a q dot square over t dot minus omega square t dot, this one, q square. Okay? So that's the Lagrangian, and in fact, if you work the equation of motion of this Lagrangian, you just get the harmonic oscillator. Q and t evolves one with respect to other. Q is a sine omega t, and so on and so forth. Now let me discretize that. Okay, I do a discretization of that, and if you don't say wow, you're not following. So I want the discrete version of this action. This is going to be a sum, okay, over n. D tau becomes epsilon. Q dot square becomes qn plus 1 minus qn over epsilon, and I want all of this square divided by t dot, so tn plus 1 minus tn over epsilon, okay, minus omega square. T dot is tn plus 1 minus tn over epsilon. Qn square doesn't need anything. What happens? Is it unbelievable? Epsilon, epsilon cancel. Epsilon square, epsilon, epsilon cancel. There's no epsilon inside. Right? Wow. This is why the Regge calculus, the Regge discretization of general relativity, has no lattice spacing. This is why the amplitude of loop quantum gravity has no parameter inside it. Right? So let's do it precisely. The same amplitude as before can be written as the multiple integral, as a limit of the multiple integral in some dtn, dqn, of the exponent of I over h bar, a sum over n, of a certain Lagrangian, which is this one, which just depend on all the qn and all the tn, where there is no epsilon, no other. This is the limit, is n going to infinity and nothing else. There's no parameter. What's going on here? Well, what's going on here is that the lattice spacing in tau, it's irrelevant because it's irrelevant. We've always said it's irrelevant. Okay, what it is replaced by? Well, it's replaced by, but we have an extra integration in dtn here, of course. So it's not. We're not simplifying our life. We're complicating life. But this integral is more complicated to compute than the one Feynman. I'm not preaching to get rid of parameter going to critical values by doing this, because this might be more complicated. But in a theory in which your background independence to start with, in which you have a parameter, your Lagrange evolve in a parameter which is not physical because of background independence, you don't have to go on a critical point. The theory goes over itself. Good. So I went a few minutes over. So let me stop here, and the next lecture we see how this connects directly to what we were doing.